The fundamental theorem of line integrals, part 3, conservative vector fields. Theorem. Let f of xy equal p of xyi plus q of xyj be a conservative vector field. That is, big F is the gradient of little f for some function little f. Also let p and q have continuous first-order partial derivatives on a domain D. Then the partial of p with respect to y equals the partial of q with respect to x. Let's do a quick proof here. Since f is conservative, which is given, that means there exists, sometimes you'll see me put the backwards E like that, there exists some f such that the gradient of f equals big F. That is, the gradient of little f equals big F, my vector field. What that means is that my vector field, big F, is the partial of f with respect to x, I plus the partial of f with respect to y, j. Because that is the gradient vector of little f. Now, since p and q have continuous first-order partials, we know that the following is true. We know that the partial of p with respect to y is the second partial with respect to little f of y x, like that. And if we were to switch the order like this, the second partial of little f, x first then y, actually it's y first then x as we write it, well, that of course is the partial of q then with respect to x. Now, why are these equal? Because when we have continuous first-order partials, the mixed partials are always equal to each other, which means the outer ones here and here must also be equal to each other. Now let's look at the converse of that theorem. It's not going to be the exact same thing. We have an extra condition here, and we're not going to prove this one, but we are going to use this one. So theorem, let big F, or the vector field f, equal pi plus qj, be a vector field on an open, simply connected region D. That is our extra condition. And suppose that p and q have continuous first-order partial derivatives such that the partial of p with respect to y equals the partial of q with respect to x. Then our vector field f is conservative. So it's basically the converse of this theorem with this extra condition of my domain or my region needing to be open and simply connected. Now, most problems we have open, simply connected regions, but just to show you what they are, this would be a simply connected region. That might not help you understand what it is, but let's do things that are not simply connected. Something like this with a hole would not be simply connected. Or even if we had two holes, or however many we might have. or if we have a region that looks like this. Which is not even connected. But assuming we have this, which is the way we usually do this, if we can show this is true, then we can show that our vector field is conservative, which means that it came from some function little f, like this. Now, in a previous video, we talked about independence of path and conservative and other things, and we talked about different ways to find conservative, or that we would in the future find ways to prove things are conservative without doing a bunch of extra work, and this is the way that we can do it. So let's take a look at an example now. Let's determine if this vector field x minus yi plus y squared j is conservative. So this is going to be pi plus qj. And if f is conservative, then the partial of p with respect to y must equal the partial of q with respect to x. So let's find the partial of p with respect to y, which is going to be -1. And the partial of q with respect to x now is going to be 0. Since these things are not equal, since the partial p with respect to y does not equal the partial of q with respect to x, we know that f is not conservative. How about another example? Consider the vector field f equals 3 plus 2xy I plus x squared minus 3y squared j. Is f conservative? If so, find the original function from which it came. So let's see. Once again, I'll put p and q. So the partial of p with respect to y is 2x. The partial of q with respect to x is also 2x, so yes, our vector field is conservative. So let's go ahead and find our function from which it came. We've done this a few times in previous videos. So I know that f, little f, is going to be the integral, the partial of f with respect to x, which is meaning we need to integrate this piece here, giving us 3x plus x squared y plus potentially some function only of y. Because when we take the derivative of that with respect to x, it would disappear. Now, if I take the partial of what we just found right here with respect to y, we would get 2xy plus g prime of y. Let me go back and fix it. I said 2xy. I did the wrong partial. It would be instead 0 plus x squared plus g prime of y. So derivative of that would be 0, and then x squared, and then g prime of y. But from above, I know that must equal x squared minus 3y squared, which tells me that g prime of y equals negative 3y squared, which means g of y must equal negative y cubed plus some constant. So now that I've found this, I can put these two things together. That is, I can substitute right there. And that gives us little f of xy is 3x plus x squared y minus y cubed plus some constant, perhaps c. I would like to do one more problem with you, finding f. We're not going to worry about conservative knot because we're going to go into 3 dimensions here. But I do want to do a problem where we have a vector field in 3 dimensions and we go back and find the original function f, such that the gradient of f is the vector field big F. So we're going to do the same sort of process. I know that f of x, y, z is going to be the integral of f of x dx. That is the partial of f, I should say, dx. So I'm going to integrate this piece here with respect to x, which will give me x times y squared, plus some function potentially of y and z only. Because when I take the derivative with respect to x, that back function g would disappear. All right, let's keep going. So now, if we were to take the partial with respect to y of x, y, z of this piece here, we would get 2xy plus the partial of g with respect to y of y and z. Now from above, I know that this is the partial with respect to y, which means that the partial with respect to y of yz must equal e to the 3z. Right, because the 2xy is already taken care of right there. So if the partial with respect to y is e to the 3z, then g of yz must equal y times e to the 3z plus perhaps some function h of z only. Right, so let's take the partial of g with respect to y. Notice that we get e to the 3z plus 0, so it matches up there. So right now, we're at the point where we have f of xyz equals xy squared plus y times e to the 3z. I'm simply substituting this back up here, plus h of z. And now I'm going to take the partial of this with respect to z, which is going to give me 3y e to the 3z plus h prime of z. And so if I go back and look up here, this of course is the partial with respect to z. And when I look up there, there is 3y times e to the 3z plus nothing, which means that h prime of z is 0, which says that h of z is simply a constant. And now I can plug this one back right there, and I can get my final function, f of xyz, equals xy squared plus y e to the 3z plus perhaps some constant c.